Hello, everyone. Sorry for all the confusion today. I'm working on it. So the test is now available. I know it's not time yet, but I just want to let you guys know I did basically I made it, but it got lost. I don't know. I'd renamed it because I took a copy that we had from an old class and just tweaked some things and changed some of the questions. And I changed the name of it, but I guess maybe my browser lost internet connection or something because when I came back, the name hadn't been changed and I couldn't find it. I'd completely forgotten about changing the name, so I was looking for midterm and it said final exam. So then I couldn't find it, and Kevin's like, "Where's it at?" I was like, "I don't know." But anyways, I found it. I've now changed the name. I put it back on the area where it says test, right under test one. It's there. It does require Respondus lockdown browser and Respondus monitor. So you need a webcam or a webcam and a computer that runs Respondus lockdown browser and can run Canvas and all that good stuff. It's in a beta form, but it supposedly can run on an iPad as well with their version of lockdown browser. So that's all set up. If you have any problems that it doesn't allow you to do it, then we can set up something at the testing center. In fact, I'm going to set it up at the testing center as if every student's going to do it, even though I suspect the vast majority will not. So that'll be starting tomorrow. You can do the testing center, and that'll allow you to do it tomorrow, Friday. It's my understanding that there's at least one testing facility that has hours on Saturday. There might even be one that has hours on Sunday. So you'll have Thursday, Friday. Well, not, yeah, you'll have Thursday, Friday, Saturday, Sunday, Monday. Tuesday's a national holiday, so we won't have it then, but you can do it Wednesday as well till 11:59 p.m. And this is all on recording, so at least y'all be able to see it again later tonight if if you didn't get all that.
Professor Younger, so is there a timeline for the test? So we can take like any time in the
Yes,
future,
you can
like
take it
3 days.
anytime. That means that you should probably not talk to anybody about it because I've tweaked some things so that one student won't get exactly the same problem as another, but generally the questions are going to be so similar. If you tell anybody or ask anybody questions about specifics, there's a good chance you're giving them an advantage over you. So just don't talk about the test until 11:59 p.m. on Wednesday. Also, even though I don't normally do this, the actual correct answers will appear the next day and they'll be available for like 24 hours. So after you take it, you can actually see not only your answers, the wrong answers, the right answers, and all that stuff, but it's only going to be for a 24-hour period. I ask just that you not share that. I mean, if you
Okay.
want it for your own records,
Uh,
that's fine, but just don't share it with other people because there's a limited number of questions that we can make up that
yeah, I just
people can
just want
solve.
just want to make sure that so that is a multiple choice question, right? It's not something that we need to write it down on paper because okay, I on my practice test I had some question that was asking me to writing down with some formula and explaining
Right.
by those formula and find out the result.
Yeah, when you go to take it, it'll have a period where they'll ask you to do things. It's text that I wrote, and like you're supposed to show a photo ID next to your face. And of course, I
Uh,
allow TCC student ID with a photograph is acceptable, not in general any other school. But Virginia driver's license or whatever state you're from, driver's license will be okay. Or a federal like military ID or something like that, as long as it's photo ID, that'll be okay. Then you're going to take your camera and sort of, if it's on your computer or your laptop or whatever, you're gonna have to show your workspace, show where your feet will be, all that good stuff. I would say probably don't have any more than 5 or 6 pages on your desk and have them spread out separately because you're going to then take them one by one and put them up to the camera so we can see exactly what's on them. Your equation sheet, of course, is only allowing the equations that are numbered plus that special version of Coulomb's law that I gave you with the vectors. So you can do all that, but those have to be shown. And then it's kind of it's kind of picky because it looks for you not wearing or not looking at the camera. If it can't see your face, it basically says that's questionable. You're allowed to wear a hat, Nora, but if you do, please, because you're wearing a hat right now, if you do, just wear it with the brim backwards. That way I can keep an eye on your eyes. So, and plus you look so much cooler that way, of course. Yeah, that would be acceptable. So anyways, go ahead and do that. You shouldn't have any problems with it. And hopefully it's giving you more time. I did notice I was in the process of working on a different version of the practice test that included only chapters 1 through or 17 through 21. That never got finished because I kept having some technical difficulties. So the practice test is still up. I just opened it back up to stay open until the 25th, but it keeps having those questions from 22. I'll try to finish it tonight and or tomorrow to have one that stops at 21, since this exam's going to be on 21. I even though I'm giving you extra time, I'm not going to include chapter 22 on it, just because I told you originally I was going to just do chapters 17 through 21. I've given you more than enough time. I think most students would probably take this in under 45 minutes.
Professor, so I just checked from Canvas and looks like the test is still locked like since like December 9th, 2022. I don't
That's
know.
probably an old version of a test, and it's one that I didn't even know was open, because otherwise it shouldn't be showing. Let me pull that up and check real quick.
Okay, thank you.
No problem. Yeah, this one is called let's see if I can see it here. Not practice. It starts with an M. It's called midterm underscore T03 underscore chapter 17 to 21. And then it says requires, dang it, does say closed, don't it? What the poop? December 9th. What the? I know I changed that. Okay, let's see. Is this even the right one? Yes, that appears to be the right one. That's weird. Okay, so I swear I just changed this 2 seconds ago, but I don't know. I'd like to say that something's going on with the Canvas or something like that, but I'm leaning towards it must be something I'm doing, or my internet connection keeps going out. Because I can't imagine it screws up this much. This has to be something with me, not the computer, and not the systems. So okay. Okay, now I've got the date change. Thanks for letting me know that, Bohan. That was helpful. Uh,
Yeah, no problem, Zinger.
so do this part there, do this part here. At least doing it in real time helps me feel a little bit of confidence that I'm doing it right. Okay, yeah, that looks right. So now I have the due date July 5th, 2023, 11:59 p.m. and it'll be available until that time as well. Actually, you can still click on it after July 5th, but then all you can do is see your results. You can't take it anymore. The time limit I give you is 112 minutes. You only allowed one attempt. Right now it's listed as the wrong category, but I'll fix that later. It seems that I thought I'd made up the categories in here, but I haven't yet. All right. So it should show open now, Bohan. Are you seeing it?
Yeah, it looks fine now. I
Okay.
haven't checked the lockdown browser, but at least there's an option I can click now.
Oh, sure. Just take a break and live on your own dime. Have a good time. Don't worry about helping me. No, I'm just playing.
I have a question.
Yes, sir.
So like the lockdown browser, I know that works on my laptop, but what does it mean webcam? Do we have to have a laptop that like do we have to download a third-party software for that, or is it
No,
through the lockdown
if you've
browser?
got a built-in camera on your laptop, it'll run with that. If not, you either have to check one out at TCC. They are borrowing from a friend that has that. The main thing is you just have to have a computer that can run Canvas, can get on the TCC internet, can run Canvas tests, can run Respondus lockdown browser, and has a camera. And I think even like a third party plug-in USB camera or something like that, even that works and it'll automatically pick it up. If you don't have that, like I said, you can check one out from TCC, or you can go to a testing center, or you can get a proctor. I've set it up where it has a password for the testing center or any other proctors that might do it, and those proctors can type in the password to let you clear off the part where you don't have to have a test. I mean, a camera. Be careful. Make sure you follow the instructions. This is weird, but I actually had a student last semester who just sort of flipped me the bird and didn't do. Yeah, double bird at that, both on the midterm and the final, and never showed me an ID. I never saw their eyes, so that, needless to say, that student ended up failing. And never contacted me, which is funny because I would have just said, it is no big deal. I know you're messing around and, here, take it again, but this time take it with the actual, with the actual camera and stuff. But they never contacted me. So I guess they were a little embarrassed. So don't do that. Please follow instructions. You're allowed, like I said, just the equations from your textbook that are numbered, and the one that I made up for you, with the RP, DQ, and all that stuff, that fancy one. You're allowed that one as well. I'm still in the process of trying to make a equation sheet for you. I might have it done before you take it. When I do have it done, I'm going to try like take question one and make up a new question one and just have a photo in there, and it'll be like a photo of the inside cover of my textbook with all the constants and conversions, and then maybe a new question two that'll have the equations in it, if I can figure out how to do that. If and when I do that, I will send out an email to everyone to let them know, so you will know not to bring any of that stuff. The only thing you need at that point is just blank paper for working. There is a possibility that one or more questions will require you to turn in your work. Specifically, like sometimes some of the more rigorous problems, like in the 241 course, I'll have people actually show me their work when they're adding vectors or something like that. So that's often a thing. Or if one of the problems requires an integral or Gauss's law or something like that, I often will have you do that and turn in your work. Not only that, I've decided that I'm going to do that on all my all my online tests from now on, because sometimes I find that, like on test one for my 241 class this semester, I went through just before class and was changing the point value so it'd be worth 100 points, but somehow the roller ball on my mouse changed the answer on like 3 different multiple choice questions, and they were just wrong, like just wrong. And therefore, what I'm doing also is you can submit your work in real time right at the end of the test. It'll allow you time to take photographs of individual pages. And like if you find a question that has, for instance, 2 right answers, meaning like sometimes, A will be 3.74 meters and then C will be 3.74 meters and they're both the right answer. You can submit that, let me know. Or if you found that the right answer was not on there at all, and you're confident you did it right and you want to let me know, that's a way you can submit that. If you think that the problem was incomplete, like it had to have some extra information on it that I didn't give you or something, then you can put that. If you, for instance, needed, let's say, the mass of the Earth and the problem didn't include the mass of the Earth, you can go ahead and call it whatever number you want, work it out. You can call it 1 kilogram if you want, work it out, and then submit that one. And not only will you get full credit, if you did it right, you'll probably get extra credit for for doing it that way. So I'm going to do that from now on. Whenever I do the online test, I'm just going to have a chance for student to turn in something if they think they did wrong. Now, be advised, I rarely have erroneous online homework questions or test questions, excuse me. So don't think this is another way for me to make the question even more hard. It's not that. It's just in case something stupid happens. So any other questions on that, anyone? Jung, did you get the gist of what was going on? I saw that you said you just got in.
Yes, I think so. So just to make sure that I'm on the same page, the midterm that was supposed to be today is going to be due July 5th, 2023
Yes.
time. And we do it through the Respondus and the webcam.
Yeah, respond us with a webcam. You can do it. If you don't have all that facility, you can check one out from the college, or you can go to a testing center and have it done. Or I think Mr. Mitchell was actually proctoring someone's test, so that's another option. I could proctor a test for you if you can't find something that works in your schedule. Just let me know.
Okay, sounds good. Yeah, I think I got it. Thank you.
Okay. Sorry for that being at the last minute. I thought it would be a nice present, especially since y'all are shortchanged on the coverage of chapter 22. So in fact, that's what I'm going to cover today is a little bit more of 22, and then I'll let you guys go. But that gives you throughout July 4th to get this done. That could mean that the next tests might pop up and be available during the same week that you're doing that one. So that's the only downside of pushing tests back for people is sometimes you might have 2, maybe even 3 tests on a given week. Not intentionally, but it's possible that you could just because you chose to, wait at the last minute or whatever. Okay.
Professor?
Yes.
Sorry to interrupt, but you said the practice tests would be available up until July 5th?
July, yeah, whatever the due date is. Let me double check.
Okay.
I think I did that already.
For like Respondus with a webcam, there's no like link to download it. So should we just go online and download the software, or is there like a code or something that we use to
To
get
the
it?
left, I think is the lockdown browser. You might be able to download it there. Y'all see off on the left-hand side, it says Zoom, then lockdown browser, then my lab and mastering.
Is that the same thing that we used our last time we took it in person?
Yeah.
Oh, so it activates our camera. We just don't know.
Right.
Okay.
Yeah, it'll do all that on its own. Yep.
There's
And
this
I'm
whole
looking, the
other thing
practice
that I've.
midterm has been changed. It's up in the
Yeah.
practice.
Okay.
But it's still
Alright.
that version that includes 22. So I apologize for that until I can get it done.
Gotcha.
Okay. And I'll keep that up. Like I said, I think I've got it listed to be available till July 5th at 11:59 p.m., which is the due date. So anything else? Anyone else?
Professor, I just want to make sure. I just want to clarify what you said earlier about like the corrections or something. So once we finish the test, we can check our answers and then we can see what we got wrong. And then if we think there's an error, we can write that down and submit it to you.
Oh, okay. So no, you won't be able to see the right answers until after you've completely submitted your test. But what I'm saying is if in real time while you're taking the test, you sense that you worked out the problem really correctly and the answer wasn't available on the multiple choice selections, then you can do it then. Or if you think you really needed to have some quantity that you weren't given, you can say, hey, I submitted an answer for number such and such, but I thought the answer couldn't be done without this figure, and here's my work. So just gives you another chance in case you feel like maybe I screwed up on something. Or if you'll notice one of the things I said, if I accidentally put a question on there that I had told you specifically was not what you were going to have to do, that would be inconsistent with my instructions, and you might want to be kind enough to say, Mr. Younger, you promised us this and you did that. That'd be a good chance for you to let me know, and I'll remember it and correct it.
Okay.
I hope I don't do that, but occasionally that's been done.
Okay.
Yeah, I covered chapter 22 and 23. Students don't generally like that.
I have a question also. Sorry. It's,
No problem. Go ahead, Drew.
is it required to submit our work at the end with the thing, or?
If I specifically request it, and right now there's currently a question where I'm specifically requesting it, then you have to.
Okay.
Now, if you didn't do the problem, you just say I didn't do the problem, and you just write no work to show or something like that. But that's often what I do when it's something I really need to make sure you guys know how to do. Like in the 241 course, I required people to show me that they know how to add vectors.
Okay, thank you.
No problem. Anything else? Anyone else?
If you ask us to show work, it's a little nerve-wracking, not gonna lie, because I like rush through my stuff and then, try to get it done. If you
Right.
ask us to show work, and we don't have like the proper work that you're looking for, will we get points off? Or like if we're correct on the question,
I'm mostly looking
whatever.
for my ability to make sense of what you're doing. And if it looks like you're doing the right things according to physics, then I'm probably going to give you partial credit even if you get it wrong.
Okay, gotcha.
But
So
if
it'd be
you
like
have
a
no work and I required work, then I might actually take off points because you just happen to remember the answer instead of actually derived it.
gotcha.
Okay, and a big hint here, some things I mentioned to you guys, you should be able to do dot products with actual vectors. You should be able to make vectors, by like subtracting two points in space, you can get a vector from. You can make it a unit vector by dividing it by its magnitude. You can also do a dot product of two vectors. For instance, I said the potential energy of an electric dipole is negative P dot E. So that's one of the things I could possibly ask you to show me your work on. The torque on electric dipole is P cross E, I think it's P cross E. So that could be another thing. Are those integrals where I did Coulomb's law in integral form for that infinitely long line, or for, one that's not infinitely long, one that's not symmetric. I gave you a bunch of variations on that problem that could be done, or for that loop of uniformly charged wire, or that circular disk of uniformly charged disk. Those are integrals that could be done. So those things are the types of things I would expect from this semester so far to be able to do. If we include chapter 22, which we didn't, that would also include surface integrals and derivations of actual electric fields using Gauss's law. Okay, so that's just a big warning to let you know, hey, these are things that I expect you to be able to do and show me your work. And I've been hinting at them, and that's why I've been showing it. Thanks for typing that down, Nora. That will help people. See if you got anything. Dot products, make vectors and unit vectors, cross products, integrals, Coulomb's law, infinite line, loop, disk. Yes. Thanks for that, Nora. Anybody else have any questions? Okay, so anybody have any questions on the material in general? I'm getting ready to start a really robust derivation of well, I shouldn't say derivation, a robust calculation of a surface integral. And the beauty of this is, one, this is a skill that, to be honest with you, you probably could walk up to a PhD mathematician and they wouldn't necessarily be able to do this, even though they have a PhD in mathematics. So it's a skill. It's a real skill that's an appropriate skill and a good skill to have. So that's kind of awesome. That being said, a good PhD mathematician would probably be able to figure out how to do it after seeing the formula or seeing it written down or something like that. But also it's just a thing that's sort of a rite of passage in terms of understanding vector calculus, which is largely what electricity and magnetism uses. I wouldn't say it's about, because in physics, the physics is what everything's about. But in order to make the understanding of the physics of electricity and magnetism understandable, you really need an understanding of vector calculus, and this is one of those things. So that's a skill that's worthwhile. So I'm going to show it to you. Not only that, it turns out that the methods that you're using for the surface integral are more or less the same as the methods you use for a line integral, which is the same thing as a path integral. It's just a matter of recognizing that you're doing a calculus process on, in the case of a surface integral, on a surface, or in the case of a line integral, along some line. And to do that, you've got to adopt the integrand, or I should say not adopt, I would say you have to alter the integrand to reflect that you're actually on that surface or on that line or on that path. So that's part of the reason why it's so important. And once you have that understanding, you might get a little bit more out of the idea of having Gauss's law that we use, where we're literally using Gauss's law to solve for the integrand on the left-hand side, which is a surface integral. So that's part of what we're doing here. So let me, I actually made up one the other day for class, and it turned out to be a good one. So I'm going to use that photograph to get it. So I am going to attempt to share my screen. And then I'm going to turn my iPad on because evidently that helps. Not positive with that, but in theory it's supposed to. I'm packed full of jokes today. That cracked me up. Stop that. Okay, so let's see here. This is not, oh, let's see that. Yep, it's doing the weekly thing where it makes me download something that I've already downloaded 1,000 times, so that's helpful. Now it's got coming up. Okay. So first thing I'm going to do is I am going to write down the actual electric field that we're using. So what I'm saying for my instructions is calculate calculate the closed surface integral E dot dA for E is equal to 3x squared z cubed I hat plus 4y z squared j hat. Okay. And I'll say on the surface shown below. Okay. So I'm going to start off by drawing a coordinate system like we often do. And there's my coordinate system. And in fact, I'm going to say my surface is going to be this shape. And then this shape. Okay. This spot right here is, well, okay. This spot right here is C. This spot right here is B. And this spot right here is A. And this is my x-axis. This is my y-axis. And this is my z-axis, which is really an overkill. Okay. So basically what we're looking at is a closed surface. That's what the circle on the integral is. The surface on an integral, if you're talking about a surface integral, the circle means that it has to be integrated over a closed surface, a surface that has a clear inside and outside. If it's on a path or line integral, then that means it's a closed loop. So it has to start at some point in space, do some crazy stuff, and then return right back to that same point in space. Mathematically, there's really no difference between it and any other integral, but it's a nice reminder for us to say, hey, we're supposed to be using a closed integral here. So that's why we often do it. I'm going to change some of this a little bit so I don't have to waste so much space. Okay. And now let's see if I can pick this up. Yes, I can. Woohoo. Who's your daddy? Who knows technology? All right. So the process that happens here is really a matter of reading the formula, which is the formula is closed integral E dot dA. I'm going to write equals question mark so you all will understand that that is, in fact, the problem. Okay. And what you have to do is you have to realize that here's my solution. In order to do a closed integral, in other words, the integral of a closed surface, what you're going to do in this case is the closed integral E dot dA is equal to the integral over one surface plus the integral over the second surface plus the integral over the third surface plus the integral over the fourth surface plus the integral over the fifth surface plus the integral over the sixth surface, like that. That's really how we're going to go about doing that. So let me label these. I'm going to label this one, and I'm going to try to draw them in such a way that when I label them, it's obvious which one I'm talking about. It won't always be, but I'm trying. So this is surface 1. This one right here is going to be surface 2. And then back here is going to be surface 3. And then up here is going to be surface 4. And then up top is going to be surface 5. And down at the bottom is going to be surface 6. So the way I'm going to solve this is I'll first take surface 1 and I'll write front. And what I have to do is I've got to evaluate each of the variables, X, Y, Z, and the electric field and the dA vector. Okay. So on surface 1, which is the front face, on surface 1, which is the front face, we have X being equal to A. On surface 1, we have Y varying from 0 to C. And we have Z varying from 0 to B. Okay. Now the dA vector is supposed to, when we have a closed surface, remember there's no ambiguity on which way the dA vector points. It always points as if it's coming from the inside out. So, and it's got to be perpendicular to the surface. So for this one, can anybody tell me what direction dA will be in? In terms of, say, unit vectors, I hats, J hats, K hats. Nora, do you know that one?
I was a little confused about your question. You're asking what
Which
be
direction the dA vector points for surface 1, which is that front face.
So like I hat
Exactly.
A or like I hat in general?
Just the I hat would be directions. You could say plus I hat or minus I hat. In this case, the right answer is plus I hat.
Okay.
Now, if you'll notice, the electric field's a bit of a problem. The electric field, when you do the dot product that you see on the integral, it's E dot dA. And what that means is the terms that are parallel with terms of dA, those terms will survive, and the terms that are perpendicular to it will not survive, right? Just because that's the way the dot product works. We use dot products in physics and engineering to choose components that are similar, and we use cross products to choose components that are perpendicular to one another. So in this case, on surface 1, we see that in fact, only the I hat term of the electric field is going to survive. And that I hat term depends on X, which we know is a constant A, but it also depends on Z. And since it depends on Z, I don't want Z to vary very much over the entirety of the dA vector. So that puts me in a bit of a conundrum as to what I'm going to use for my differential area element. So what I am going to do, you might not come up with this immediately, but I suspect you could after a little period of time. I'm going to say my differential area element is that little green bit I drew there, whose thickness is dz, and whose width, I think you can see, is of course c. So I'm going to write this as c dz. Does that make sense? So that's sort of the most complicated stuff, is to make sure you choose your dA right. Now, if you were in Calc 3, you would have already covered double integrals and triple integrals and so on and so forth, which is the more natural realm to do this, in which case you could have just said dz dx I hat, and that would have been fine. But I'm not allowed that freedom for you guys. I can't teach you double integrals, okay? So it makes it a little bit harder the less math we can do. Now I've done everything. I've done the X, the Y, the Z, the dA. Now all I got to do is the E. And now I'm using the value of X, the value of Y, the value of Z to write out what E is on surface 1. So on surface 1, we have 3x squared Z cubed. The Z is going to vary, so I have to leave that as Z, but the X is A, so I'm going to write 3a squared Z cubed I hat, like that, plus 4. Now, in this case, the Y is going to vary and the Z is going to vary, so I can't do anything but write Y Z squared J hat as that. If you had a similar scenario for a surface integral, for instance, and you were integrating from x equals 1, y equals 0, and, or excuse me, x equals 0, y equals 0, and x equals 1, y equals 1, you could do it along the equation, along the line y equals x, and then all you do is either replace x with y and leave everything in terms of y, or replace y with x and leave everything in terms of x. But if you were doing it along, say, y equals x squared, then you're going to replace all of your y's with x squareds. So that's sort of what we're doing here, is we're finding relationships that we can specify on here. In this case, there's nothing more I can do than that. So now I'm going to say the integral over 1 is 3a squared z cubed I hat plus 4y z squared j hat. There's my E. Then there's a dot product, and the dot product is c dz I hat dotted with that electric field. You can see I'm going to integrate over dz, so I'll put that in the range of integration in a second. But first, I'm going to use the linearity of the dot product. The linearity of the dot product basically means that if you had, let's say, some number C1 times vector A plus some number C2 times vector B, and you dotted that with vector V, then what that means is you can write it as C1A dot V plus C2 B dot V. In other words, you can pull the scalars out in front of the dot product and then just let the dot product act on the individual vectors. So when I do distributive property, that's going to give me 3a, oops, I should probably write back in blue. That's going to give me 3a squared c z cubed dz, and then I hat dot I hat. Now, the other thing you'll remember about your dot products is A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them when they're tail to tail. Okay. So from that, we could reach the conclusion, and this always looks to me like a drunk owl. I kind of like that, right? So this is going to be 1, because the magnitude of I hat, having a hat on it, must be 1. 1 again, because the other one is also 1, and then cosine of 0 degrees, because clearly I hat is parallel to I hat. Therefore, you just get 1 for that. Now, the other part of the integral is plus. Now, in this case, I'm going to do 4 cy z squared j hat dotted with, oops, I should have not written that yet, dz. Now I should write j hat dotted with I hat. Now this looks more like, you know, a drunken owl that's had a stroke or something, because it's got one eyeball bigger than the other. In this case, it's 1 times the cosine of 90 degrees. And of course, that gives you 0. Whereas this one just gave you 1. Okay. So I ultimately have that the integral over 1 is the integral from z equals 0 to b of just 3ac cubed dz, which equals 3/4 a b to the 4th c, and that should be it.
Is it a calc thing for the vector value to just be 1?
We use unit vectors a lot, and they do it in calculus as well as vector calculus and stuff like that. It's just the most convenient vector you can use because it gives a direction without a magnitude.
Okay.
So that's why you have that hat in there on occasion. It's they call it a basis, BASIS, which is basically I hat, J hat, and K hat are a basis for the 3 space. But there's also ones, like I said, for spherical coordinates that would be R hat, theta hat, and phi hat. So yeah, it is a typical thing that we'll do. So I'm going to underline this 1 time because that represents the answer for the integral of over surface 1.
Is it supposed to be a squared?
Was yes, I dropped the 2. Thanks for catching that. That would have been a pain in the butt later. Yeah, because it was an above. Yeah, I did have a squared above, and everything else looks okay. Okay. All right, so that's the first part. Now the second part, and you can see this is not a fun day at the park or anything, right? There's a lot of crap to go on here, but it's all very doable. It's just a matter of making sense of what each part is. So in this case, I'm going to now do the integral over surface 2. So I'm going to write 2, and 2 is the right face. So I'll write RIGHT next to it. And just to separate this from the solution, I'm going to put the solution as a double underline and then just underline these as once. So the integral over 2 is going to be, again, oh, I don't want to write that yet. I hadn't done my variables yet. Okay, so the first thing I want to do is figure out what x is on surface 2. Everybody hopefully can see that x is going to vary from 0 to a. Y, on the other hand, is going to be a very specific value. Y is going to equal what? Anyone? Anybody know what Y is going to be?
C.
Exactly. Okay. So we're just going to say Y is C. And you can imagine, for instance, when we get around to surface 4, Y is going to be 0, and that's going to make life pretty easy, right? All right, now we're going to do Z. And I think you can see that Z varies from 0 to B. So I'll put colon 0 to B. So you can see by doing this, this allows us to quickly figure out what our ranges of integration are, as well as what variables we need to restrain when we go to make our differential area element, all that good stuff. So can anybody give me the direction of dA? And I'm technically going to call this dA2, which I should have also called this electric field 1 and dA1. Just because it differs from one surface to the next. It's not wrong to not do it. I just wanted to include it for completeness. So can anybody tell me just the direction of dA for surface 2?
The J hat.
It's the J hat, yes. And now looking at it, you see that the J hat's going to survive. That's the term that's going to survive in the electric field. And the electric field had a J hat term that's 4YZ squared. So Z is again changing, which means I should probably use the exact sort of thing for the differential area element for this one, where the thickness here is going to be dz. That way z only varies by an infinitesimal amount from one side of dA to the next, and the other part is the distance a. Okay, well actually I should probably start it right here. Let's get this drawn right here. Okay, so clearly this area, this dA element is going to be A times dz, and it's going to point in the j hat direction per Nora's suggestions. Does that make sense to everyone? Now the electric field on surface 2 means I've got to evaluate the variables. Well, the variables I have are 3x squared z cubed. X is clearly varying, as is z, so I can't do anything with that one. So I'm going to say 3x squared z cubed I hat, which luckily for us, Mr. Younger made this up in such a way that that wouldn't be a problem. In other words, we wouldn't have to do a double integral. Plus, now this other one's 4y, so this is going to become 4c times z squared j hat. So that's the electric field evaluated on surface 2. Really all we had to do for that one to make it surface 2 was replace the y with c. So now I'm going to do the integral over 2 of 3x squared z cubed I hat plus 4c z squared j hat, all that dotted with a dz j hat, and I'm going to use the linearity of the dot product again. That's going to give me the integral of 3a x squared z cubed dz I hat dot j hat plus 4a c z squared dz j hat dot j hat. Okay. And we can see now the integral is actually going to take place over z, and I'm going to integrate from 0 to b. And that was the same thing I integrated from last time. Yeah, I did write that out, just making sure. So that's z equals 0 to b. You can see, hopefully, again, that this is 0, whereas this one becomes 1. So I end up getting the integral of z squared dz from 0 to b. That's going to become 1/3. So I now have, I should switch back to blue. I have 4/3 a c. Actually, let's do it a different order. I like to keep my alphabet in play. So this is going to be a b cubed c, and that should be it. So that's the actual integral over surface 2, which I'll mark by having 2 underlines in green. So that will remind me that's surface 2. Any questions on that one?
So we're naming ZB because it goes a distance B. So we define Z as B.
B is actually supposed to be a number, like it could be 3 meters, but I just did it as
Okay.
B. Yeah, so I'm integrating from z equals 0 to z equal 3 meters, say.
That makes sense.
Okay.
Okay, thank you.
So you see, it's not that hard. It's just it's a piecemeal process that you do step by step by step, not unlike the integral problems I was working last time, where the first step is define dq, the second step is define rp, the third step is define rdq, and then find rp minus rdq, which is rp dq, put it all in the integral, look for any symmetries, that sort of thing. All right, let's try surface 3, which is the back. And if you look at surface 3, I think y'all can already tell me what's the dA direction for surface 3. Anyone want to give me that one?
It's gonna be the same thing as the first one.
Except it's negative.
Oh, yeah.
Yeah, because remember, it's always got to point out. So in this case, it'd be pointing in the negative x direction, so it's negative I hat. That means only the first I hat term of the electric field is going to survive, and that first term is x squared z cubed times 3 times I hat. So we know that on that back surface, x is equal to 0. So that makes life a little easier for us to figure out. And it tells us that we can use as our differential area element that same shape again. Where the height is going to be dz and the width is going to be c. So I'm going to go over here. I'm going to say surface 3, which is the back, has x equal to 0. It has y varying from 0 to c, and it has z varying from 0 to b. Then it has dA equaling negative c dz I hat. Okay.
Professor, why is it negative again? I'm not really understanding how the direction works.
Okay, so the convention is if you have a closed surface, there's no longer any ambiguity as to whether, let's say this right here is my surface. Okay. You could do some surface here, but that's all very ambiguous because, it's got a y component, it's got an x component. There's no good reason to use any particular vector. But if you say it's going to be perpendicular to that surface, then that reduces it to only two possibilities, this or that. So if you just have a surface in space that's not a closed surface, there is an ambiguity, but the ambiguity is only plus or minus. Once we convince ourselves that we have a closed surface, then we can make a convention, and the convention can be that the vector will always point out of the closed surface, or a convention can be that you point in. The convention that's been decided upon is that it points out. So in this case, the back of the box, if you want to point from the inside of the box.
Oh, okay. Yeah. All right.
That makes
That
sense?
makes much more sense. Thank you.
No problem. And that is our I hat direction, and it's negative I hat for that reason. Okay. Now we're going to evaluate E, which is really nice. And again, this should technically be called DA3, just like this should technically be called E3. And if we look, E was supposed to be 3x squared Z. So that's 3 times 0 squared Z times I hat. And then the other term was 4yz squared plus 4y z squared j hat. So that's what the electric field has to be on that back surface, which means our integral over 3 is going to be 0 I hat plus 4y z squared j hat dotted with negative c dz I hat, which gives us the integral from z equals 0 to b, obviously at surface 3 still, of 0 times negative c dz times I hat dot I hat plus 4yz squared times negative c dz j hat dot I hat. That is 0 because they're 90 degrees. This is 0 because that's 0. So the answer is 0 for surface 3.
Professor, would it be wrong for us to say that the differential element is negative c dA?
Yes, just because C is understood to have units of meters and dA would be meters squared. Now, are you saying dA like the differential of
Yeah.
the number on the line?
Yeah, like
Yeah, that would be understandable, but the tradition is that you normally go with the coordinate directions,
oh, I
dz,
think
dx, dy.
I messed up in the beginning because I was putting dA as the differential element width, so that's
Gotcha.
wrong.
Yeah.
Yeah, all right, that makes sense. Thank you.
Yeah, that's just a little technicality related to, no experience doing this weird of a thing before. So that's perfectly fine. I wouldn't worry about it at all.
Yeah,
All right.
okay. Thank you.
So now I'm going to do surface 4, and this time I'm going to get you guys to do it. Surface 4 is actually the left side. So what I'd like you to do is go ahead and write out what X is, what Y is, what Z is, and let's see if we all agree. This is really a chance for you to see if you know how to do what we're doing. I'm going to turn it back to this page so you can look at it. We're now doing surface 4, which is that left face. And what I want you to write down is what is X. You either write it equals and then some number, or a colon and then some range. And then what is Y, and then what is Z. See if you guys can do that. And sorry for the guys, correct? That's just a phrase I use. if you want, if you already are up to speed enough where you think you can get the dA, go ahead and do that too. And if you're up to the speed to get the E field, go ahead and do that too. I'm going to go ahead and write out the answers for the X, the Y, and the Z. So for X, we had that X is going to vary between 0 and I think that's what I called A. Yes, A. For Y, that's going to be just equal to 0. And for Z, it's going to vary from 0 to B. Okay, if you guys are ready, go ahead and go for dA. See if you can get it now. I'm going to give you a couple seconds before I write down my answer.
In
And
the
then,
last one, do you mind explaining why it was negative again for the DA?
yes, not a problem at all. So the convention is when you have a closed surface, we define the vectors, the dA vectors, to point out of the closed enclosure, right? So on the front face 1, it should point out of the page. On the right face, it should point to the right. On the back face, it should point into the page. On the left face, it should point to the left. The top face, it should point up. And the bottom face, it should point down.
Oh, okay.
Does that make sense?
Yeah.
Yeah, so it's just a convention that we decided on, and it actually works really well because it turns out the closed integral of E dot dA turns out to be equal to the charge enclosed divided by epsilon naught. If that charge is positive, then the electric fields all point out of the box, and therefore you get a positive number. So that's why they chose that particular convention. It does work out really nicely. All right, so hopefully everybody's had time to figure out what dA is going to be. I'm going to go over here and say dA is going to be this surface right here that has a width A and a height dz. So I'm going to say negative, oops, I'm going to write it in the color blue. I'm going to say negative A dz j hat. And it's j hat and negative because it has to point to the left and the y-axis points to the right. Hopefully everybody got all those. Did anybody not get some of those and need some help with the X or the Y or the Z or the DA? So it looks like everybody did okay. Let's go ahead and do E4 now. E4 is us evaluating E with these conditions that we just wrote down. The E is supposed to be 3x squared z cubed. So that'd be 3. X is going to vary and Z is going to vary. So I can't do anything with those. But then the J component of the electric field is 4yz squared. So that's 4 times 0 times z squared times j hat. The z varies, so again, I couldn't do anything with that. But you can see that I'm clearly going to get 0 on the j hat term, which, by the way, happens to be the only thing that's going to survive the dot product. So we're going to get 0 on this again. So the vast majority of these things, when you're doing these special ones, just to make sure you know how to do it, they're going to have a lot of easy cancellations that you wouldn't really have to write all this stuff down, but it's good to just until you can take the training wheels off. So now I'm going to say the integral over surface 4 is 3x squared z cubed I hat plus 0 j hat, all that dotted with negative a dz j hat. Clearly, I'm going to integrate from z equals 0 to z equals b. So I can put that up there, but it's not really going to matter because ultimately I'm going to get the integral from 0 to b of 3x squared, actually 3ax squared z cubed. There's going to be a negative in front of it. And there's going to be a dz, and then there's going to be a I hat dot j hat. And this, of course, is going to be 0 plus 0, plus 0 times negative a dz times j hat dot j hat, which is going to be 1, but that's not going to matter because I already got a 0 there. So the answer is, in fact, 0, and that's for the fourth surface. So I'll go 1, 2, 3, 4. Just so I can quickly find each of the terms and add them up. Now I'm going to do surface 5, which is the top. Go ahead and let you guys come up with X, Y, Z, D, A, and E. So for the top surface, find X, Y, Z, D, A, and E.
Could you flip it back to the second page real quick? Thank you so much.
I'm going to start filling this in. If you're trying to work it out, don't cheat. Just go ahead and try to work it out yourself because that's really what's helps you more than anything else. That one's a little tricky. Okay, hopefully everybody got the same thing I did, unless I made a careless mistake. Anybody have any problems seeing how we got that? We should watch that. No one sees any errors with that, Bohan or Nora or anybody? Elron? Okay, so the integral over surface 5 is going to be 3bx squared I hat plus 4b squared yj hat dotted with cdx, k hat. And technically, since that's a dx, I'm going to integrate it from x equals 0 to x equals a. And that's again over surface 5. So this becomes 3b squared x squared I hat dot, oops, I don't want to do I hat yet. 3bx squared times c dx, and then I hat dot k hat plus 4b squared y c dx. And in this case, it's j hat dot k hat. Okay. Clearly, j hat dot k hat gives me 0. Clearly, I hat dot j hat gives me 0. So the answer is 0. And to indicate that that's the fifth, I'm going to go 1, 2, 3, 4, like that. Okay.
Does it matter which way you orient the integral inside the closed surface? Like,
No.
could you? Okay, so you could say like y equals 0 to b, and then have it from, like a dx.
Yes,
dA.
yes. Yeah, that would
Okay.
be fine. Yeah, the main thing is if you had the electric field, which could depend on X, Y, or Z, if one of those variables in the electric field component varies over the differential area element, then you've got to do some kind of averaging process to represent that true value of X. That's the beauty of having a double integral, because you could just call the double integral dx dy, and or the dA you could call dx dy k hat or something.
Gotcha.
But that's a lot easier once you get to the point where you can do double and triple integrals. All right, so we got one more part, which is surface 6. And I am just going to write it right here. And surface 6 is the bottom. And what I'm going to do is realize that the bottom is the same as the top. So x is going to be 0 to a. Y is going to be 0 to c. Z, however, is going to be 0. dA is going to be negative c dx k hat. The negative because it's got to point down. And then the E, and this is technically 6. Just like this is 6. Now, if you notice, the electric field has a Z in each term, in both the X component and the Y component. And since Z is 0, that's just going to give you an electric field of 0. Whoa. Of 0. Dang it. Stop it. Of 0 I hat plus 0 J hat. Therefore, the integral over V just becomes the integral of 0 dA, which is just 0. And I'll say that's 1, 2, 3, 4, 5, 6, like that. So the ultimate answer is just going to be this 3/4 a squared b to the 4th. So the closed integral E dot dA is going to be 3/4 a squared b to the 4th c plus 3/4 a to the a squared b to the 4th, and then 4/3 a b cubed c. Plus 0 plus 0 plus 0. That's 5 plus 0. And there's really nothing you can do with it. These are all unlike terms. You could factor out a common C if you wanted to, but that ain't gonna do us any good. And that's the ultimate
Thought
answer.
that second term was, I thought we were using Z. I thought it was Z cubed C.
We were,
I
but
might
you
be,
evaluate Z at the endpoints. So the Z became the B.
okay. Oh yeah, gotcha.
Okay. So that is actually the final answer of that god awful problem. Any questions on that one?
Could you go back to how you did the sixth side?
Yes. So the actual, I'll go to the very
Mhm.
first page where you see what the E was. The E was 3x squared z cubed I hat plus 4y z squared j. Okay. However, on the sixth face, that's the bottom face, z has a value of 0.
Right. Yeah.
See, 3x squared
So
times
in
0
both cases, it
cubed is
cancels
going to
out.
give you 0. And the same thing with the j hat term.
Yeah.
Wouldn't matter in anyway because the k hat's
Gotcha.
perpendicular to both of those, and what it gave you 0 anyways. All right, so it's 6:45. You guys go ahead and take a 10-minute break. Be back at 6:55, and I'm going to finish up chapter 22. Of course, I'll take questions not only during the 10-minute break, but when you get back as well. So go ahead and do that, and I'll be sitting here the whole time in case anybody has any questions. I see you guys are answering in the chat way more than I noticed, so thank you for that. Maybe I should say you folks. Uh-oh. Friday the 30th is the anniversary of the Tunguska explosion in 1908 over North Russia. Cool. I have a lot of random stuff I put in my calendar. Gettysburg, July 1st. The Apollo mission had a fire on June 28th. I had the Stonewall uprising / riot, whatever, on the 28th as well. Cool. All right, got about 3 more minutes. All right, it's about time to let's roll. So I took time to write some stuff down here. This is Gauss's law. It says the closed integral of E dot dA, which we now recognize is the net flux, which is sort of a count of the electric field lines leaving a closed surface. And what it says is the net flux exiting any closed surface has got to be equal to the charge enclosed by that surface divided by epsilon naught. Last time I, in some sense, derived it. I wouldn't say I technically derived it. I calculated it for a spherical charge at the origin and ended up getting that the answer was Q, the charge that I had at the origin divided by epsilon naught. And then I argued that that is, in fact, the reality. So that gave us the right-hand side in general, even though I did it for a highly specific case. So the way we're using Gauss's law mostly in this text and in this chapter is we're taking this version, this integral form of Gauss's law, and we hypothesize based on symmetries and our knowledge of Coulomb's laws for the electric field, we hypothesize the electric field, both its magnitude, well, what variables its magnitude depends on, as well as what direction or directions it points in. We hypothesize that, insert that into the integral, and then because of the symmetries, the actual magnitude, since we're taking a dot product, you only have the magnitude left. The magnitude will pop out, and you'll get on the left-hand side a electric field magnitude, basically a symbol representing its magnitude times an area is equal to some amount of charge enclosed over epsilon naught. That allows you to solve for that magnitude. And it turns out we can actually get electric field strengths based on that. That's one of the ways you can use the integral form of Coulomb's law. And that's mostly what we're doing here. But you'll also notice that your book uses it for other things. So for instance, the idea that a electric field has to be zero inside of a conductor, electrostatic conductor, that is, under electrostatic conditions, that gives us an idea that any charge on a conductor will force itself to move out to the outside surface of that conductor. And that allows you to conclude sort of neat things like if you have a charge, let's draw this to give you an idea what I'm talking about. Let's say, for instance, you have a conductor like this, okay, and this is three-dimensional conductor, so it's sort of spherical, if you will, and inside there's a little cavity, okay, and that's also a let's say spherical cavity. If you put a charge plus Q in there, then you can actually take Gauss's law and say, okay, I'm going to draw a Gaussian surface right just inside of the conductor like this. And because that left-hand side closed integral E dot dA, because the electric field is zero in a conductor, you get that that's zero. So that means that Q enclosed over epsilon naught has got to equal zero. So that tells you that what actually happened with this is this forces a charge of negative Q to appear on the inside surface of that cavity. Because the Gaussian surface, the black one that I drawn here, even though I just drew it in 2 dimensions, that's inside the conductor, and under electrostatic situations, you can't have any electric field inside of a conductor. So the E dot dA is going to be zero everywhere. So the left-hand side of Gauss's law is zero. That means the right-hand side of Gauss's law is zero. And that means the charge enclosed has a total of zero. Well, we already know there was a point charge inside whose charge was positive Q. So in order to counteract that, we must have a charge of negative Q. And since I can draw this Gaussian surface as close to the conductor surface, the inside of the cavity surface as I want, but still inside the conductor, then that means the charge negative Q has to actually appear on the inside surface of that cavity. If you now went out and drew another Gaussian surface outside of here, okay, in that area, you could actually reach the conclusion, well, the total charge inside for this part here must be 0. So there must be another charge, because I got plus that and that. You could use that, for instance, to infer things about other charges. In this case, it's not so helpful. But if for instance, you had let's say a conductor like this. Whoa, that's bad. Okay. Let's say you had a conductor like this, and you took a Gaussian surface just inside of there. Under electrostatic conditions, the E field is 0. So the closed integral of E dot dA has got to equal 0 all inside of that. If the thing had a charge of positive Q, then that means the charge plus Q would appear completely on the outside surface. So that's some of the stuff you can do with Gauss's law, in addition to using symmetries to solve for the electric field. So it's not just that. And in fact, I should say that the lion's share of the work done in electricity and magnetism, at least when you have the ability to solve differential equations, is done by Gauss's law in differential form. So it's a lot more powerful than you'd have, than you'd believe, based on just what we did in this course. So I'll just say that now. So that's some of the stuff we do with Gauss's law. So let me start off by doing that nastiest of all nasty problems that we did on the first day of integrals with Coulomb's law. So I'm going to use the same coordinate system, and I'm going to say, let's say we have a coordinate system right here. I'm going to say this is my z-axis. And I'm going to say that this right here will be my, this right here will be my y-axis. And this right here is going to be my x-axis. So there's x, there's y, there's z. You can see it's a right-handed coordinate system. That's important. I'm going to take an infinite line of charge and orient it along the z-axis. And I'm going to assume that that charge is uniform and goes down to negative infinity and goes up to positive infinity. Lambda equals dq over dl is a constant. Remember, lambda is the charge per unit length. It's something that has units of coulombs per meter. And what I'm saying is that's a constant. So if you pull out a meter of this charge, you'll get a certain amount of coulombs on it that you can measure. And then let's say it's 1 coulomb, then your lambda would be 1 coulomb per meter. If you, however, pulled out a millimeter, then what you'd end up getting is, in fact, a millicoulomb, and that would be a millicoulomb per millimeter, which is the same thing as a coulomb per meter. So that's what we're talking about here. I am going to choose to have a point P right out here along the y-axis, and that's going to look very specific, but it's actually quite general because of the symmetry of this problem. You can look at it from any side. In other words, I can rotate myself and look along the x-axis in the negative direction, or I can go along the x-axis in the positive direction, or I can go along the y-axis in the negative direction, or the y-axis in the positive direction, and in all those cases be looking back at the same wire, and it will look identical. So by acting like the point that we wish to know the electric field at, P, is at a distance r along the y-axis, we're actually considering it being along all possible directions radially outward from it. And in fact, it's better to think of that as not the y direction or not the j hat direction, but the r hat direction from cylindrical coordinates. Okay. So remember, does everybody recall what I'm talking about? The r hat direction and cylindrical coordinates? Does that make sense to everyone? Okay. So what I'd like to do is find the electric field at P using Gauss's law. Okay. So here's my solution. I know the closed integral of E dot dA has got to be Q enclosed over epsilon naught. Okay. Now, what I'm going to do is choose a very specific Gaussian surface, and I need to choose that Gaussian surface so that, and listen to these words very carefully. This is the most important part about how to solve it, even though it doesn't take any math. It just takes some configuration and some thinking in space about how the electric field's behaving. I think you can look at this charge distribution, which is just a string of charges along the z-axis, and say that if I go any distance away from the z-axis, let's say 1 meter, and I go allow the universe to rotate around me, around that z-axis, all of those locations at r equals 1 meter is all going to have the same electric field strength. Do y'all agree with that? Okay. And would you also agree that in all of those cases, the electric field would point away from the wire in space? Okay. So that's sort of the definition of the r hat direction. So that's a good idea about how we're going to make some hypothesis. I'm going to actually change something on this just so I can fit this in. So I'm going to move this. I apologize for this. It's not going to be a problem for you guys, I don't think, but oops, let's not do that. That just makes me look dumb. Okay. Actually, that all makes me look dumb. I hate that. So I'm going to put that as my y-axis. I'm going to put this as a distance r, and this is the point P. Okay. The reason why is I really want to fill a Gaussian surface up here. So I'm going to choose for my Gaussian surface, I'm going to use this green right here. And what I'm going to choose is a Gaussian surface that's a soup can. Notice that's about 3 away. That's going to be about 3 away over here. And a soup can, in order for it to be helpful to Gauss's law, has to be, in fact, a closed surface. So I have to have the top and the bottom as well. So notice that by making that a soup can, I've actually made the outer soup label, the surface on which the electric field is 1, a constant. So does everybody see that the electric field strength will be a constant everywhere on that soup can's label? And 2, it will be exactly parallel to the dA vector at each point on that soup label. Y'all see that part? Now, if you were fortunate enough to have had the second semester of calculus, then, or the third semester actually, then what you'd realize is this part right here is the differential area element, and that differential area element points radially outward like that, and that's the dA vector, which equals dA. I don't need to go in any more detail than dA because I'm never going to integrate the left-hand side. That's a key thing. You're never going to integrate the left-hand side. You're never going to have to do real calculus on the left-hand side. It's always going to be the electric field times an area, or it's going to be 0. So in this case, I'm going to say dA in the r hat direction. Now, if you really wanted to know, that dA is r d theta times dz. and that's fine. It's just you don't need to know it, but I give it to you just in case you're familiar, and it might actually help you better understand by knowing that. You can see, of course, that the width of that little pizza slice is r d theta from our s equals r times theta, and you can see the height of that little postage stamp is in fact dz. That's why I say dA would actually be r dr or dz d theta. Okay, now here's my hypothesis. I'm going to say hypothesis. And the hypothesis is that the electric field is actually going to be something that only depends on the distance r, but points in the radial direction. So this is the whole reason that I showed you those coordinate systems that are, sort of esoteric and not that well understood, except for weirdos like me. Okay. And other weirdos like us engineers and scientists and stuff. So it's not because I wanted you to use the coordinates of cylindrical coordinate systems and spherical coordinates day in and day out, but I did want you to understand what the symbols mean. So by saying this is E of r hat, in cylindrical coordinates, you know exactly what I mean. That little r hat is a vector pointing radially outward. So that's my hypothesis. So now I'm going to say, and this is the way you do it. Remember, we have a left-hand side of the equation. We have a right-hand side of the equation. The left-hand side looks really complicated, and it's supposed to be some fancy integral. But as I said, you're never going to do any calculus on that left-hand side. You're going to get maybe more than one term, but all of the terms are going to be E being a constant times some area are 0. So what I do is I say left-hand side, and then I write that the left-hand side is the closed integral of E dot dA. And in this case, that's going to be the integral of E of r hat, dotted with dA r hat, because that's the differential area element that I dealt with. Now, there's also another differential area element, actually 2 more that I have to deal with, and I'll deal with that in a second. So this is the integral over the soup label. So I'll just label it S period, L period for soup label. Everybody understand what I'm saying when I'm saying this is a soup can? Okay, well, there's also a differential area element up here at the top that you might recognize, looks like this. And of course, this guy would be dA top is equal to dA k hat. And similarly, this differential area element, which I'll call dAB for bottom, is going to be negative dA k hat. Okay, so in order for me to do a closed surface, I have to integrate the top, the bottom, and the soup label. So I'm now going to say plus the integral over the top of E of r hat dot dA top k hat. I really should subscript this T, because obviously I'm going to have a different dA here. If you want to know, the dA is in fact going to be r d theta dr, or r dr d theta. And then plus the integral over the bottom, which again equals E of r hat, dotted with, in this case, negative dA bottom times k hat. This is where we're going to make use of the linearity of the dot product again. And I'm going to say we basically have the integral over the soup label of E of r dA r hat dot r hat plus the integral over the top of E of r dA top r hat dot k hat plus the integral over the bottom of E of R dA bottom. And actually, I should probably call this a negative because remember it had that negative sign in it. So I'll say minus, and then this is going to be R hat dot K hat. So that negative came from the negative that you see there in that last term right there. Everybody get that? Can anybody tell me what R hat dot K hat is?
Shouldn't that just be 1?
Think again. K hat points parallel to the Z axis, and R hat
Okay. That should be 0 then.
exactly. And R hat has only I and J components, is what I was going to say. But yes, that's right. I figured you were thinking right, just made a boo-boo. So those two terms are going to go to 0. This is what I meant by the left-hand side is always going to be the magnitude of the electric field times some area. Okay. So the left-hand side is ultimately going to be equal to E of R times, now we're actually doing this over the entire soup label. So the entire soup label, if I cut that Campbell's soup label vertically downward and laid it out, it would make a rectangle. And the length, or excuse me, the width of that rectangle, if I drew this right here, for instance, to say, I'm going to change colors real quick. This length right here, I'm going to say is H. And clearly what we can see here is the radius is R. So can anybody tell me the height of that soup label? And can anybody tell me the width of that soup label? Would everybody agree that if I cut that soup label off, it would make a rectangle? And in terms of a circle or a cylinder, what would be the distance along the top edge of the soup label? Is there a word that you can tell to describe that distance?
The circumference.
Circumference. That's what I was shooting for. So you know the length is 2 pi r, right? And then what's the height?
Isn't it like DH?
It's the whole h that I put there. But yeah, you're right. Okay.
Oh, I thought we were taking a differential element.
Yeah, no, we're doing the whole thing at this point.
Okay.
So you get 2 pi r h is the area. This is literally just the integral of dA, because once you did r hat dot r hat, I'm gonna switch colors again. Oop, I don't want pink. Okay. Once I did r hat dot r hat, that's just 1. So I end up getting this whole thing just becomes E. Remember, we're actually integrating it on a surface of fixed radius r. So E of r is a constant. And I end up integrating dA. So the integral of dA is just A, which is the soup label. That's why I had 2 pi r h. So that's the left-hand side. Now the right-hand side of Gauss's law says that it is Q enclosed over epsilon naught. If this particular wire has lambda coulombs per meter, and h is the height and r is the radius of the soup can, how much charge is inside the soup can? I'm not getting answers on chat. Ooh, let's do that, everybody. Let's see. So can somebody tell me how much charge is in that Gaussian surface?
Would it be 0 inside? I'm not entirely sure, but since
The
we
original statement that we made regarding this was that it had lambda was a constant, and that's the dq over dl. In this case, that'd be dq over dz because it's along the z-axis.
Mhm.
So, for instance, what I said was if the number was 1 coulomb per meter, if you took a meter of it, it would be 1 coulomb in that. So what do you think you'd have to do with that lambda, which we're pretending we know, to get the total charge?
integrate it.
In some sense, but it's actually easier than that because it's the integral of a constant.
Oh.
So it's the integral of some constant lambda times dz from z equals, let's say, negative h over 2 to positive h over 2.
So you just do, well, it becomes 0 then because you're going to be finding the average between those values once you take the integral.
Almost.
I might not be understanding it though.
That's okay. No, that's you're thinking right. So, and in fact, the right-hand side of Gauss's law is often just going to result in the integral of q dv, or excuse me, the integral of rho dv, or the integral of sigma dA, or the integral of lambda dl. So I will take an extra step and I'm going to write 1 over epsilon 0. In this case, I'm going to say the integral of lambda dz, because lambda is the charge per unit length that I told you about, and we're pretending we know. And we're going to integrate that. I'm going to assume that I centered up my Gaussian surface so that the bottom of it is negative h over 2, and the top of it is h over 2. Now, this is actually way more complicated than it needs to be. I'm just trying to convince you that this is the right answer. Since lambda is a constant, what does this integral become?
Just the integral of dz.
Exactly. So you can say lambda times the integral of dz from negative h over 2 to h over 2.
Just h then.
Exactly. So you get lambda over epsilon naught times h, because it's going to be h over 2 minus negative h over 2, which is obviously h. So the total charge enclosed is just lambda h. That's what I was trying to get you to get.
I see. I was thinking that you were subtracting the positive value, but then it like the math didn't make sense. So I need to go back to algebra. Thanks.
Yeah, that's okay though. I mean, the main thing is I want you guys to be following to some extent. So it's great when you actually speak up and have a little error, because you can be sure if you have an error, someone else does too. So does everybody understand that normally when the density, the charge density, in this case, it's a linear charge density, when that's a constant, you just multiply the density times whatever it's of. So for instance, I said the DQs are always, DQ is equal to either lambda DL, or it's equal to sigma dA. Oh, I should write this way, sorry. dA, or it's equal to rho dV. So if you actually know that it's a charge per unit area, then all you have to do, if that charge per unit area is a constant, all you have to do is multiply that constant sigma times the area A. If it's a charge density like rho, all you have to do is multiply that rho, if it's a constant, times the volume. And in this case, since it was a constant linear density, all you have to do is multiply that lambda constant times the length. Okay, so now we got the left-hand side and the right-hand side. So I'm going to say left-hand side equals right-hand side. And that gives us E of R times 2 pi R H is equal to lambda H over epsilon naught. And remember our original hypothesis, I'm going to change colors real quick. Our original hypothesis right here says that the electric field, I can solve for this E of R, which is the actual magnitude, but I know the magnitude times R hat is the actual electric field. So I'm going to go ahead and say E is equal to, when I solve for E of R, I get lambda. Notice the H's cancel out. I get lambda over 2 pi R or 2 pi epsilon naught. So lambda, ooh, don't want to do that. I get lambda over 2 pi epsilon naught R in the R hat direction. And that's the actual answer, which hopefully you guys remember is exactly the same answer we got when I did the calculus method using the integration of Coulomb's law. Any questions on that? So that's kind of nice. It's a lot easier than, for instance, that Coulomb's law integral form that I did before. Any questions?
So on the exam, technically we're only through chapter 21. What if we have like an infinite chart, like a question that asks to find the E field? Can we use Gauss's law to find
No,
that,
you're
or
not
do you want us
supposed to.
Okay.
In fact, if I did something like that, I would probably specify using Coulomb's law for electric fields vector form or something like that. Then you have to use that specific form. But you can certainly use it since you understand, if you understand Gauss's law, to check your work.
Okay.
I definitely recommend that. And that's the kind of thing that if I saw you checked your work, I might even give you some extra credit, even if you fudged up the first part.
Okay. Thank you.
No problem. All right. So everybody got that? Have some sense of what's going on with that one? So that one is a long cylinder. Remember, I said the symmetries are long cylindrical. And really what long means is if the end is at least 10 times further away than you are from it, then you can consider that long. If it's 100, it's really a pretty good approximation. If it's 1,000, it's an amazingly good approximation. So for instance, if you're next to a kilometer long wire and you're 1 meter away from it, then yeah, that's a really good estimate to assume that's infinitely long. Okay, that's a superly good excellent. So we've done now the long cylindrical. What I want to do next is the spherical, and then I'll do a planar. Okay. So there's a couple ways you can do the spherical. What I'm going to do is let's do the spherical in a very specific way. I'm again going to draw a coordinate system. Okay, this is going to be my x-axis. This is going to be my y-axis. This is going to be my z-axis. And I'm going to soup it up a little bit. I am going to draw a circle. Like that. Dang, that turned out good. Okay. The circle has a radius. Actually, let's move it down because it didn't come out as good as I would have liked it to come out. But anyways, let's say, whoa. Now that's not what I wanted. Okay, that looks pretty good. Okay. Now what I'm going to do is say the radius of the circle is big R. Like that. Okay. And what I'd like to find is find the E field using Gauss's law. For R less than big R and for R greater than big R. That's what we're going to try to assume here. What I'm going to do is I'm going to say the sphere has a uniformly charged volume of total charge Q. Okay. So what that means is we're pretending like we know big Q and we're pretending like we know big R. And we're looking for the electric field at small r, where small r can be smaller than big R or bigger than big R. Okay. So let's do my solution. My solution is the closed integral of E dot dA is equal to Q enclosed over epsilon naught, and uniformly charged means rho is equal to a constant, which equals, make sure you can follow this. I'm going to write Q. I'm going to put a 3 in front of it and then a 4 pi r cubed. Can anybody see why I have that 3 there and the 4 there? This is some old school geometry stuff.
So like the volume or surface area or something?
Yeah. The volume of a sphere is 4/3 pi r cubed, which, trust me, you'll never forget once you cover Calc 3 and you do it with triple integrals. Okay. So now by me stating that, I also know rho, not just Q, because I've just defined rho in terms of Q and R. So that's kind of helpful. So let's start off with my hypothesis. If you'll notice, this sphere has spherical symmetry. And what we learned about spherical symmetry is that the strength of the magnetic, or excuse me, the strength of the electric field only depends on how far away you are from the center of the sphere. In other words, R from spherical coordinates, and it points radially outward, which means in the r hat direction. Again, in this case, for the spherical coordinates, not for the cylindrical coordinates. So does everybody agree with that and understand what I mean by saying that? Actually, I don't even have to make it piecewise. I'm just going to say E is equal to some E of R hat. And in this case, this is the spherical R hat. Remember the last one, it was the cylindrical R hat. And the spherical R hat, I could actually write as R hat is equal to, let's say, cosine theta, sine phi I hat plus sine theta sine phi j hat plus cosine phi k hat. That's the spherical one. Okay, in other words, it has X, Y, and Z components, whereas the cylindrical one was just cosine theta I hat plus sine theta j hat. Okay, so that's our hypothesis. Now I'm going to draw a Gaussian surface. I'm going to choose green again, and I'm first going to go with the idea that R is less than big R. Okay. Notice I didn't put any stipulations on my hypothesis for R. I suspect R, my hypothesis for the electric field is always going to have a magnitude that just depends on how far away I am from the origin. and points radially outward, whether R is less than big R or greater than big R. So that's what I'm going with here. In this case, I'm going to take a green Gaussian surface, which will be a concentric sphere, like that, and only not like that. I'm going to make it like pretty and awesome and stuff, but okay, evidently it's not going to let me move this little sucker. Oops. Stop changing this. Stop it. Okay, I'm going to get rid of that. Oop. Why won't it let me move? There you go. Okay. Okay, so that's supposed to be a concentric spherical shell. And that spherical shell, of course, has a radius little r. Okay, that's my Gaussian surface. And as I said, and these words are the more important part, that is a sphere. Okay. So the left-hand side of Gauss's law says the closed integral of E dot dA is equal to the integral of E of R hat dotted with, now dA is going to be, for instance, you could take a little tire patch, if you will, on this spherical shape and say that dA is equal to dA R hat. We just have the convention that it has to point outward from the closed surface, so that's certainly fine. So I'm going to say dA R hat, which again, the linearity of the dot product allows me to pull all the scalars out in front. Not only that, the fact that I'm integrating this on a sphere of radius R tells me that I can pull the E of R out in front, and I can say E of R times the integral of dA R hat dot R hat. And of course, R hat dot R hat is just 1. So I ultimately get the answer is E of R. Again, that's just E as a function of R. I'm saying the magnitude E of R depends only on R. And the area, in case you are not aware, the area is the surface area of a sphere, and that is 4 pi R squared. Everybody follow that? So notice again, the left-hand side just became a magnitude of the electric field times a area. Again, you might have multiple terms, but all the terms are either going to be E times the area or 0, or you're doing it wrong. So now I'm going to do the right-hand side. And the right-hand side is Q enclosed over epsilon naught. Well, this is equal to 1 over epsilon naught. And technically, it's always, like I said before, it's always going to be the integral of lambda dL. I'm looking at this right here. It's either going to be the integral of lambda dL, the integral of sigma dA, or the integral of rho dV. And in most cases, you can get away without doing an integral. I'm just going to write the integral right now, just so you'll know. Since we said it, the charge was uniformly distributed throughout the volume, that tells us we're using a rho. And I even wrote up there that rho is equal to a constant. So what I end up doing is saying Q enclosed is equal to the integral of rho dV. But rho is a constant, so you can just say rho over epsilon naught times the integral of dV. Well, that's just rho over epsilon naught times the volume of the sphere. And does anybody recall what the volume of a sphere of radius little r is? Y'all agree with that? Okay. So that's nice, but we already defined what rho was, so I can make that even simpler. I can say 1 over epsilon naught, and then the rho is 3q over 4 pi r cubed times 4/3 pi little r cubed. And notice what happens. This 4 cancels out with this 4. This pi cancels out with this pi. This 3 cancels out with this 3. And I'm ultimately just left with q enclosed over epsilon naught is q over epsilon naught times r cubed over big R cubed. So now I can say left-hand side equals right-hand side. That's going to give me E of R times 4 pi R squared is equal to Q over epsilon naught times R cubed over big R cubed. And you can see now that R squared completely cancels out and leaves just a 1 there. So we get that E, again, going back to my hypothesis, E is going to be Q over 4 pi epsilon naught big R cubed times little r times R hat. And this is for R less than big R. So we see the electric field is actually linear. It's not even linear, it's proportional. So it's some number times R. It doesn't even have a plus B in terms of linear. So for R less than R, it's a linear function, specifically a proportional function. Now we do for R greater than R. And in this case, we're going to again do a Gaussian surface that is a sphere. And this time the sphere is going to have a radius larger than the radius of the sphere. And in fact, it's going to have a radius equal to big R. So quickly rolling through this, I'm still using the same hypothesis. I'm going to say left-hand side is going to just be equal to the closed integral of E dot dA, which by now you should realize is just going to be E of R times 4 pi R. Oopsie, I wrote big R. That's not supposed to be big R. Everybody make that correction there. I don't know why I wrote big R, but I did. And let's make it this color. Okay. So 4 pi R cubed. Well, let's not make it green. And then the right-hand side is even easier because in this case, the charge enclosed is just the total charge Q. So Q enclosed over epsilon naught is just Q over epsilon naught. So for R greater than big R, that's a lot easier, right? Now I just set left-hand side equal to right-hand side. And I get E of R times 4 pi R cubed, or R squared, sorry. Let's make sure we correct that. Let me correct it there too. Okay. Remember, area has units of like square inches, square meters, something like that. So that should be a R squared, not an R cubed. Now that's going to be equal to Q over epsilon naught, which I think you can see is now just Coulomb's law. So E is equal to Q over 4 pi epsilon naught R squared R hat for R. And if you notice, if we consider the case of little r equals big R, we will see that we can now write this as less than or equal to and greater than or equal to R. And that's our answer here. So if I wanted to plot the electric field strength as a function of R, I could come out here and write big R. And then I could come over here and write Q over 4 pi epsilon naught R squared. And since it's linear for R less than big R, I would get a straight line from the origin to it. And then it falls off like 1 over R squared, which is like that. So that's what the electric field strength looks like as a function of R. Any questions on that? All right, well, I didn't get enough done that I wanted to. I will tell you this, so pay attention to these words. These notes are going to be put up on my Google Docs within about 10 minutes, so you don't have to worry too much about writing them. The words I'm getting ready to say is very important. If this was a conductor, technically this has to be a non-conductor, in fact. But if this happened to be one where they said find the electric field for R less than big R and for R greater than big R for a conductor whose total charge is Q, you would immediately recognize that that entire charge Q is going to go around to the outside surface. Okay, so it's just going to be on the outside surface. What that means is the closed integral of E dot dA is still going to be E of R times 4 pi R squared. But for R less than R, the Q enclosed over epsilon naught is going to be 0. So the electric field inside of the conductor will be 0, at least till you get to big R. Then when you get to R greater than big R, you're going to have the same Gaussian surface I drew here, but now all the charge big Q is going to be on the outside edge, and your Gaussian surface is just outside of that. So again, the left-hand side of Gauss's law becomes E of R times 4 pi R squared, where R is the little r. And the right-hand side is going to become Q over epsilon naught. So you get the exact same expression, E equals Q over 4 pi epsilon naught R squared R hat for R greater than R. So in that case, for a conductor, what you're going to have is out here a radius big R. Your electric field is going to be 0, 0, 0, 0. Whoa. And then it's going to jump up to right here. Hey, what does this? Well, you're probably not even seeing what it's doing. But this is Q over 4 pi epsilon naught R squared. And at this point, it's going to fall like 1 over R squared. Like that. Notice there's a discontinuity. The electric field at R, big R, is both 0 and Q over 4 pi epsilon naught. That discontinuity is equal to Q over 4 pi r squared divided by epsilon naught. Can anybody tell me what Q over 4 pi r squared is? Y'all recognize that as any kind of symbol we've used in the past? Let's say one of these symbols. So which one of these symbols is Q over 4 pi r squared?
I want to say sigma.
And then you'd be exactly right. Okay, so the discontinuity is going to be sigma over epsilon naught, which your book talks about. Okay, now I still haven't done one where the charge density is proportional to R or proportional to R squared, which again is a non-conductor. I haven't done one for an infinitely long plane or for an infinitely large plane. That ends up becoming sigma over 2 epsilon naught, not sigma over epsilon naught. But you can see those in the book, and I think you have a plenty of examples between me thoroughly covering this and you looking at examples in the book. You have plenty of examples to get chapter 22 homework done. That being said, I'm still going to work some more examples on Monday. Okay, so you folks are free to go. Thank you for coming, everyone. I'll wait for the last person to leave in case anybody has any questions. Does anybody need these notes? Can I close them right now? In other words, if not, I'm gonna if you don't need me to, I'm gonna go ahead and close them and wait to get out. But otherwise, will be posting them. Thank you, Jung, for coming up with the sigma as well. You and Nora. So I just stopped sharing the screen because it looked like nobody needed it. Again, waiting for the last person to leave and then I'll split. But other than that, y'all have a good one. Make sure you get your test done, your midterm. Let me know if you need anything. Yes, John wants to see that last page for a second. Let me do that again. It'll take a couple seconds for it to load back up, but you should see it in a second. Maybe. There, you got it. Okay. So there's the last page, Joan.
Professor, could you maybe quickly re-explain how we got the Q enclosed? Because I thought we would be using the volume of a sphere. And like I
Right.
get how that's kind of integrated, but not entirely sure.
Yeah, so for R less than big R, we actually had a fraction of the charge
Mhm.
Q. The Q is the total charge on the whole sphere, but the whole sphere is not enclosed in that inner Gaussian surface that's the little green sphere. Okay, so one way you could look at it is you could
Right.
say the total charge, big Q, over the total volume, 4/3 pi big R cubed, is equal to the Q enclosed, which you just call Q, E, and C, divided by 4/3 pi little r cubed. If you did that, you'd get the same expression that I'm showing right here, Q r cubed over r cubed. So that's how you get it in the case for
Gotcha.
R less than R. In the case of R bigger than R, it's just a matter of being so
Yeah.
simple, you're kind of confused by it. And specifically, the Gaussian surface is larger than the charge. So the entire charge Q is inside of it. That's why I didn't have to do anything special. I just wrote Q.
Oh, okay. All right.
Does that make sense?
Gotcha. All right.
And
Thank you very
notice I
much.
gave you that proportionality
Yep.
way. That's another way you can do it. I don't want you guys, I mean, you can if you like integrating, but I don't want you guys to feel like you got to integrate all the time, which is sort of what I did in this right-hand side that you see right here for R less than R. Really, you could have got that, like I said, by sitting q over 4/3 pi r cubed equal to q enclosed over 4/3 pi little r cubed. That would give you the exact same expression.
I see. Thank you.
No problem. Hopefully that helps. So this is like a really, well, it's an attempt to really do well an explanation of how to apply Gauss's law in a spherically symmetric situation where the charge is uniformly distributed throughout. And then it ended with a case where we're considering a conductor. And with a conductor, the charge can't be uniformly distributed throughout, at least not in an electrostatic situation, which we'll learn about later. So in that situation, all the charge will reside on the outside. You can think of it as like, well, conductors means the charges are free to move. So if you have any free electrons floating around in there, they're going to do their absolute best to get as far apart from each other as possible, which means they're going to get on the outside edges. So that's another way of thinking about it. When you do that, then that automatically tells you Gauss's law says the Q enclosed is going to be 0 until you get outside the sphere. So that's why you're going to have an electric field be 0 out until you get to big R. And remember, these videos will be posted, so you can always go back and, you know, sometimes I speak and I try to talk slowly, but sometimes I say a lot of important stuff in, you know, just a few syllables or a few sentences. That is a common thing to happen. So I don't want you to feel like you're not smart enough or you know, you're bothered by it. All you need to do is realize, oh, well, I've got access to a recording. I can just go back and listen to it slowly until I get what he's saying. So definitely make use of that. I'm trying to talk as slow as possible, but sometimes I blow over, you know, people, and I don't mean to. It's just a matter of that's the way you talk. Anybody else have any questions? Y'all seem to have followed this really well. Several people were putting in answers, multiple people at least were putting in answers. Multiple people were asking good questions, so that's a good thing. Don't feel bad if you're not getting it. It is sort of Greek looking right now, and that's fine. But go back, watch the video of me working this one individual problem and slowly make sense of it. Pay attention to the words I'm saying more so than the symbols I'm writing, and hopefully it'll make a little bit more sense. And then when you see more examples like your textbook does, or more examples that I do on my YouTube channel, or more examples I do in face-to-face meetings, or say Zoom-to-face meetings, hopefully I'll get a better understanding.
Professor Younger,
Yes.
I had a question.
Go for it.
I just have a question about this extra credit question. I guess I'm answer, but just want to make, I'm not trying to ask you how to do it, just want to make sure that my understanding is right on those, like, because there's a lot of things to read. I'm not sure if I understanding
Gotcha.
The information right. So one of this extra credit, the ratio I got was like 2.268 times 1039 power.
Yeah, that's right.
Okay, the other one, I got the distance was like 0.2002849 something meter. Like 0.2
You're talking about the ratio of the Coulomb force to the gravitational force for a proton and an electron in a hydrogen atom, right? That's the extra credit you're referring to?
No, I'm talking about the ratio I just said was like 2.26 10 times 1039 power. I'm asking the other ones, like, how far is too far?
Right.
Is that like 0.2 meter?
Yeah, that one I don't know the answer off the top of my head. What I do is I just look at it, and what you're going to do is use the formula that we just derived in the previous example, which is lambda over 2 pi epsilon naught r. That's the magnitude of the electric field. That's if it's infinitely large. If you integrate it from negative L over 2 to positive L over 2 instead of from negative infinity to positive infinity, you're going to get a formula that still only has a perpendicular component. It doesn't have a z component in the way we drew it today. But it'll have a definite finite end at L over 2 and negative L over 2. And it'll differ a little bit from lambda over 2 pi epsilon naught r. What you're
Can you use
calculate those two? Yeah, go ahead, Bob.
yeah, instead, I mean, if it's not like infinity large, can you use the regular formula E equals KQQ, I mean KQ divided by R squared, because we already had the R value and also the density, so we can just calculate what's that.
No, you can't use the Q because this that K Q1 Q2 over R squared that we know from Coulomb's law for the force, that's only for either a spherically symmetric charge or a point charge. So when you have a distributed charge like along a line, you actually have to do the calculus to do it.
So that's only for the point charge. Okay, that's probably I got it. I probably got it wrong.
Yeah,
I was kind of
okay.
confusing, like why there's two different formula there. I saw it just one for the infinity long.
Right.
Okay.
So when you do, if you look at the example where I did it infinitely long,
yeah, I saw that
is integrating from negative infinity to positive infinity, and I use symmetry to just do twice the integral from 0 to infinity. In this case, you can do twice the integral from 0 to L over 2. And everything else is exactly the same, but the answer will come out to be the right answer for a finite wire.
Okay,
and
so
all you're trying to do is find out how much they differ.
So every time, so if you look at the electrical field, like not just a point charge, then you had to use the calculate one.
Yeah, the calculus integral one.
Okay. I didn't know this before. That's why I got it probably wrong.
Yeah, that's okay. And a lot of people make that mistake. It's perfectly normal. So, but now you know it's you have to break it up into our infinitesimal continuous charge distributions dq, and that dq can be lambda dl, or it can be sigma dA or rho dV.
Okay, and also from the formula, it looks like say for the like infinitely long, so the electrical field is only matters with actually the what's it called, the density.
Yes, the charge density along the line. So it's like
So it's like it doesn't really matter. That's how long that thing is, or it's only because. Okay.
Yeah.
So I kind of don't really understand. Is that because like how to understanding that part? Like it doesn't matter with how long that thing is.
It's like if you imagine a wire and every centimeter you put one electron and tied it down, then you would have a charge of negative 1.602 times 10 to the negative 19th coulombs per centimeter. That would be lambda. Now, when you're trying to calculate the electric field, let's say, 10 centimeters away from the center of that wire, then as those electrons get further and further away from the point that you're calculating the electric field at, they become less and less important. So ultimately, it just works out to matter how much dense it is.
Oh, I see. Because your R value is get really, really huge at that point.
Exactly.
Okay, I see. I was kind of just couldn't imagine like why it's not why like doesn't matter about how long that is. Okay.
Right.
Thank you for explaining to me.
No problem, Bohan. It's kind of interesting if you go into a classroom. A lot of time they have those long tubes of light, those incandescent or fluorescent lights that are tubes.
Yeah.
The brightness of those falls off like 1 over R, just like the electric field of a line charge falls off like 1 over R. Whereas if you had a light bulb, that's like a point charge, and the brightness of that light falls off like 1/r². So if I go 1 meter away, I have one brightness, but if I go 2 meters away, it drops by a factor of 4, the brightness.
Oh,
Whereas
okay.
when you have a long string of light, it drops only by a factor of 2 in going from 1 meter to 2 meter. So that's why they actually use those long fluorescent tube lights in stores and stuff like that. It makes it more bright all the way down to the floor.
Right. Yeah, all my workstation had those kind of like.
Yeah, and they will sometimes put diffusing plates on top of them. And they're starting to look like a infinite surface. And what we find out when we do an infinite surface with Gauss's law is that the electric field strength is independent of distance away. So those plates actually make it like it's not getting any darker as you get closer to the floor, at least within small distances.
Wow.
So that's just kind of a neat little sidebar that can help you remember that.
Yeah, thank you, Professor Younger.
No problem. See you, Bohan.
Yeah, see you. Oh, by the way, I'm sorry. One last thing that I checked my grade. The first in-person test, like my
Is it
grade
still
still
showing wrong?
yeah, still showing wrong. Haven't been checked.
Okay. Yeah, keep on me on that. I'll try to remember to do it right after I finish uploading this video. But if I don't, yeah, let me know again. I apologize for not
Oh,
doing it
yeah,
on
no
time.
problem. Thank you.
All right. You have a good one.
Thank you. Have a nice weekend.
You too. Josiah, you waiting for me, bud? I think he's still here. He must not be. Nope, it's just me. All right. See you, everybody. Bye-bye. Bye-bye.